In the previous video, we proved that the running time of the merge sort algorithm on a sequence consisting of n elements is big O of n log n. In this video, we will show that this bound is essentially optimal. We will do this by showing that any correct sorting algorithm that sorts n objects by comparing pairs of them must make at least n log n operations asymptotically in the worst case. Once again, we say that a sorting algorithm is comparison-based if it sorts the given objects just by comparing pairs of them. We can imagine the following situation. We have n objects that look the same, for example n balls, but have different weights. And we also have pen balance. And this pen balance is our only way to compare pairs of these balls. And our goal is to rearrange these balls in order of increasing weights. So, for example, the two sorting algorithms that we already considered, namely the selection sort algorithm and the merge sort algorithm, are both comparison-based algorithms. So, for example, the selection sort algorithm at each iteration finds the minimum object, the minimum value in the remaining part of the array. And it does so exactly by comparing pairs of objects, right? Also, the merge sort algorithm is also comparison-based algorithm. So it first splits an array into two halves, and then it needs to merge the two resulting arrays. And when merging the resulting arrays, it also uses comparisons, right? So we take the first two elements of two sorted arrays, we compare them, and based on this comparison, we take one of these elements out of one of these two arrays and put it to the resulting array. So this is a formal statement that we are going to prove. It says that any comparison-based algorithm that sorts n objects has running time at least big omega of n log n in the worst case. So put it otherwise, we can say the following. Assume that you have an algorithm that sorts n objects by comparing pairs of them. It can be the case that for some input sequences of n objects, your algorithm performs less than n log n operations, say linear number of operations. However, it cannot be the case that your algorithm always sorts in time asymptotically less than n log n, meaning that there must exist sequence of objects on which your algorithm will perform at least big omega of n log n comparisons to sort such sequences. Any comparison-based algorithm can be shown as a huge tree that contains all possible sequences of comparisons that can be made by this algorithm. For example, here on the slide, we show a simple algorithm that sorts three objects. So it starts by comparing A1 and A2. If A1 happens to be smaller than A2, then we proceed to comparing A2 and A3. If A2 is smaller than A3, then we already know the permutation of the input three objects in non-decreasing order. Namely, we know that A1 is smaller than A2, and we know that A2 is smaller than A3. So we can just output the following permutation, right? If, on the other hand, A2 happened to be at least A3, then at this point we only know that A2 is greater than A1 and A2 is no smaller than A3. So at this point we know that A2 is the maximal element among our three elements. However, we still need to compare A1 and A3. So we do this comparison, and based on its result we output either this permutation or this permutation. Well, this was the case when A1 happened to be smaller than A2. However, we need also to consider the case when A1 happened to be at least A2. So we proceed similarly in this case. So this is just a toy example for an algorithm, for a comparison-based algorithm comparing three objects, sorting three objects. However, such a huge tree can be drawn for any comparison-based algorithm. So at the top of this, at the root of this tree, we have the first comparison. At its children, we will label just the next comparison that is made based on the result of the first comparison, and so on. So each internal node is labeled with some comparison, and each leaf is labeled with a permutation of n input objects. A simple but crucial for this argument observation is that in this tree we must have at least n factorial leaves. And this is because we have n factorial different permutations of n input objects, where n factorial is defined to be the product of n, n minus 1, n minus 2, and so on. So, and why is that? Why we must have any possible permutation as a leaf in our tree? Well, this is just because it is possible that this permutation is a valid output, is the right output of our algorithm. So, for example, on our previous slide, on our toy example, we have 3 objects and there are 6 possible permutations of these 3 objects, and there are 6 leaves in our tree. For example, one of them is 2, 1, 3, and it says that the second element is the smallest one, then goes the first element, and then goes the third element. And indeed, there are cases when this is the right answer. Right? So when the input data consists of 3 objects, such as the second element is the smallest one, the first one is the next one, and the third element is the largest one. Right? So once again, in our huge tree, which corresponds to our comparison-based algorithm, there must be at least n factorial leaves, because each possible permutation must be present as a leaf in our tree. Okay, so on the other hand, the maximal number of comparisons made by our algorithm corresponds to the depth of our tree. So the depth is defined as the maximal number of edges on the way from the root to the leaf, to some leaf of our tree. So when this is exactly the maximal possible number of comparisons which our algorithm makes. So now we would like to show that D must be large in our case, must be at least big omega of n log n. And we know already that our tree contains many leaves. I mean, n factorial is a function that grows extremely fast. Okay, so intuitively we would like to show that if a tree has many leaves, then it has a large depth. And at least intuitively it is clear. If you have a tree of very small depth, then it must have just a few leaves, right? But we know that it has many leaves, at least n factorial leaves. To formally show this, we need the following estimate. The depth of a binary tree is at least the binary logarithm of its number of leaves, or equivalently 2 to the depth is at least its number of leaves. Well, this can be proved formally, but let me just show you this informally. Let's consider a tree, for example, of depth 1. So in this case, D is equal to 1, and it is clear that the maximal possible number of leaves in a tree of depth 1 is equal to 2, right? So now let's try to understand what is the maximal possible number of leaves in a tree of depth 2. For example, this is a tree of depth 2. This is another tree of depth 2. It has 3 leaves. And this is a tree of depth 2 that has maximal possible number of leaves. In this case, it is 4. It is 2 to the d indeed. And intuitively, it is clear that to have a tree of depth d that has maximal possible number of leaves, we need to take a tree which is a full binary tree of depth d. Right? And this tree has exactly 2 to the d leaves. So the maximal number of leaves in a tree of depth d is 2 to the d, which proves that 2 to the d is at least L. Okay, so the last step that we need to show is that if we have n factorial leaves, then the depth of our tree is at least big omega of n log n. And we will show this on the next slide. It remains to estimate log of n factorial. We're going to show here that log of n factorial is at least c times n log n, which means, in other words, that log of n factorial is big omega of n log n. To do this, we express n factorial as a product of 1, 2, 3 and so on, n minus 1, and then write logarithm of product of these numbers as a sum of their logarithms. So log of n factorial is equal to log of 1 plus log of 2 plus log of 3 and so on plus log of n. So this is a sum of n objects. Let's just throw away the first half of these n elements and leave only the second half. So in this second half we have n over 2 elements, and each of them is at least log of n over 2. Right? So these are logarithms of numbers which are at least n over 2. So we have n over 2 elements. Each of them is at least logarithm of n over 2. This allows us to conclude that the whole sum is at least n over 2 times log of n over 2. And this is in turn big omega of n log n for a simple reason. So log n of log n over 2 is equal to log n minus 1. Well, this grows like log n, right? Because log n is a growing function and 1 is a constant. So log n minus 1 grows as log n. N over 2 grows as n, right? So this is up to a constant factor, this is just n. So n over 2 times log n over 2 grows like n log n. Okay, so this concludes our proof, and this concludes the proof of a fact that any comparison-based algorithm must make at least n log n operations in the worst case. Once again, another conclusion is that our merge sort algorithm that we considered in the previous lecture is asymptotically optimal. In the next video, we will see an algorithm that actually sorts n given objects in time less than n log n. Actually, in time, just in linear time, in time bigger of n. However, it will sort the n given objects knowing something about these objects. It only sorts n given objects if these objects are small integers, and we will sort them without actually comparing them to each other.